Okay. Hi, everyone. Today we have a speaker, Matthew De Furio. He's in an LSF Astronomy and Astrophysics postdoctoral fellow at UT Austin. And started in 2003. Oh, yes, and completed PhD in the University of Michigan. And I believe that you worked with Mike Meyer. He's a member of James Webb NIRCam team and NIRIS science teams as well. And he leads several HST and JWST programs, basically to explore free-floating planetary mass objects, very, very low mass object multiplicity, and some kind of fundamental limits of star and brown dwarf planet formation processes. And this is very relevant and important work that you're presenting. So Matthew, take it away, please.
All right, thank you so much for that introduction. So today I want to talk to you about my work investigating star formation through the very low mass end of the IMF and through stellar and substellar multiplicity. For a very brief overview of what I'm going to be talking about, here's a short simulation from the StarForge collaboration. This is just a simulation of a star forming region, and essentially we start with a turbulent gaseous medium that has various overdensities and underdensities. And as we start zooming in, we see that these overdensities will begin to contract gravitationally, producing filamentary-like structures. And eventually, those filamentary-like structures will have small little pockets that will collapse and start to produce protostars that then accrete, building up their final mass. But then also ejecting material back into the star-forming region. So you can start to see some of these protostars here in the white. These are protostars that have collapsed, and we also start to see some feedback. And that feedback is important because it will also influence the rest of the star-forming region. So it can influence the amount of turbulence that's in the medium. It can influence gas temperature, all of that kind of stuff. And you see a little bit more feedback that's going to pop up in the bottom left over here. So the environment, feedback, all of these things are important in our understanding of star formation processes. Now, one of the outputs of the star formation process is the initial mass function. And this is just a characterization of the total number of objects as a function of mass within a given population. Here, this is from a review from 2010 that shows the mass function in various associations and clusters and the field. And what we see is that regardless of environment, so whether you're in a loose association like these blue triangles or a dense cluster like these red circles, we don't see any large-scale differences in the IMF. Now, I want to point you to everything higher than -1 because there's incompleteness at lower masses. But what we see is this salpeter slope, this characteristic salpeter slope with a peak around roughly 0.2 solar masses. And that doesn't seem to really change regardless of the environment in which we look. Now, theory predicts that the limit of this process should be somewhere around 1 to 10 times the mass of Jupiter, or about 0.1 to 1% of a solar mass. And this limit occurs when a core becomes opaque to its own cooling emission. So as the gas tries to cool to continue to collapse, if it becomes opaque, it can no longer collapse and will just be a pre-stellar core that does not produce any compact object and eventually just disperses. So the questions that I'm interested in are, what is the opacity limit? And what is the shape of the IMF down to the opacity limit? One of the other things, too, is that there are various properties that could impact the very low mass end of the IMF. I just showed a simulation that had increased turbulence, increased feedback, and those factors could play a role potentially in what we observe. Now, the IMF has been characterized pretty thoroughly in the past, especially in the solar neighborhood and some nearby star-forming regions. What they find, this is a survey from Davy Kirkpatrick in a volume-limited 20-parsec sample that characterized the population of MLT and Y-dwarfs. and fitted a power law index to the mass function down to their sensitivity limit, which was around 10 Jupiter masses, or about 0.01 solar masses. And for the rest of the talk, I'm going to be talking about the mass function in linear space. So the previous image I showed you was in log space. Now we're going to talk about in linear space, where we define the mass function as dn dm goes as m to the minus alpha. So in the field here, in this analysis, they had identified for roughly below the substellar limit a power law index that increases from the substellar limit down to their 10 Jupiter masses with a power law index of about 0.6. Right, so we have this increasing mass function of more sources in linear space, again, linear space, as we go down to lower and lower masses. However, they can't really probe lower masses because they just get very faint given the age of the field. And so that's why we want to explore this question in young star-forming regions. One of the things about star-forming regions is that because they're very young, things that are Jupiter masses, roughly Jupiter mass regime, are their hottest, right? They're still contracting, so they're at their hottest, meaning that they are at their brightest and easier to detect. So we want to target these young star-forming regions, and this is one of the GTO programs from the NIRCam science team. I led the analysis in this region, NGC 2024, or better known as the Flame Nebula. And this is the PI of this program is Michael Meyer, my former thesis advisor. And the main concept is to basically just stare with NIRCam in the core of this cluster with really long exposures across many filters. So we had these deep 2-hour integrations for 8 different filters from 0.7 to 5 microns in order to detect these free-floating objects. And one of the reasons we need JWST and that we can't use something like HST, for example, is because these regions, when they're really, really young, have a significant amount of extinction. There's a lot of dust. So we need something that can be very sensitive in the 4 to 5 micron regime to peer through the dust. And also the peak of the SED for these Jupiter mass objects is also around 4 to 5 microns. So by using NIRCam, we can both peer through this significant amount of extinction in this region and also detect these free-floating Jupiter mass objects. This is a mosaic from HST with the WIFC3 IR instrument. This is the same region, the Flame Nebula. And WIFC3 IR is only sensitive out to the H band. So there are definitely a lot of portions of this cluster where you don't really see any point sources. So up here, for example, there's a significant amount of dust that's blocking a lot of the light coming from sources inside of here. So this is our NIRCam footprint. And here is our color combined NIRCam image of NGC 2024. The blue in this image come from the filters around 1 micron, and the red come from around 4 to 5 microns, and everything in between. And there are things that point out that pop out right away. So in that same portion of the cluster that I pointed to where you don't see any point sources with HST, we see a bunch of red point sources with JWST. Same when we look towards the bottom of this region, we see a lot of this knotty nebular material with JWST that we did not see at all with HST before. Now I'm going to zoom in a little bit so that you can see more detail in these images. They're such amazing images. I have to spend a little bit of time just showing them to you. There's so much complexity and so many features in this region that make really analysis of these sources actually pretty difficult. But you see a lot of outflows. You even see some cavities. You see filamentary-like structure all over the place. You can even see a proplet in here if you look hard enough right down there where my cursor is. And on top of that, we see this knotty nebular emission over here on the left, and we just see nebulosity absolutely everywhere. But what I'm most interested in is identifying faint point sources. So if we start zooming in on one of the portions of this image, kind of the bottom right portion, hopefully you start seeing some of these faint point sources popping out of the data. So they're obviously, they're a little harder to detect by eye, but you start seeing sources down here, and over here that should be our candidate Jupiter mass objects. If I go back to the full image, because this region is so complex, because there's so much extended emission, if we were to run typical point source detection techniques on these data, they just get thousands and thousands of false positives. So they basically identify point sources where all of this nebulosity is. So we had to come up with our own way in order to identify point sources and differentiate from nebulosity. But instead of doing kind of a by eye, what looks like a point source thing, we actually came up with an automated detection routine, which not only allows us to identify real point sources, but it also allows us to define our completeness very thoroughly across all of the data that we have. So essentially saying, what is our magnitude limit as a function of fraction of the area of the images. In addition, there should be a lot, or not, maybe not a lot, but there should be contamination from background stars. So even though there's a significant amount of extinction in this region that should shield us from a lot of background objects, there's still variable extinction that you can see all over the place. You can see just variable nebulosity, and that also means that there's variable extinction. And so there is definitely an opportunity for stars in the galactic field to just kind of shine through these low regions of extinction and resemble these faint point sources. So we came up with a way to remove contaminants. We did this by assuming a galactic population model taken from Trilegal and an estimate of the extinction at the specific position on the detector that we were observing, and then calculating the likelihood that a source was either a likely background object or a likely cluster member. And from the roughly 100 point sources that are all the 100 unsaturated point sources that we found in these data, we were able to identify 48 likely cluster members. Here I show just a few examples of these very faint free-floating Jupiter mass objects that we detected that are circled here, 1, 2, and 3. And so now we have our sample of about 48 likely cluster members. Next, what we want to do is characterize the mass function. So we have a handful of sources that we have identified as likely members. Next, what we want to do is characterize the mass function in this region. Here on the right, I show a color map that is essentially our completeness. And so through that automated routine, we're able to identify where we should be able to detect sources above background in the entire, across the entire image. And that's our color map. So in the yellow, we're able to identify everything with that combination of color magnitude. And as we go bluer and bluer, we're less and less sensitive. The red points are our likely cluster members. The red line is a 1 million year old isochrone from the ATMO 2020 evolutionary model. And these black squares represent various masses of sources from this evolutionary model. So you can see that we're sensitive down to about a half a Jupiter mass object through no extinction, or a 1 Jupiter mass object through about 30 magnitudes of extinction. And the lowest mass thing that we believe is a likely cluster member is around 3 Jupiter masses. Now, I don't know if you heard the conversation we were having a little bit before we started, but we did find point sources that were at fainter magnitudes that populated the parameter space over here. However, they were almost all consistent with being background objects given our model. And so our likely population is what we see here. So we really think that the lowest mass thing that we believe is a likely cluster member is around 3 Jupiter masses. Now, we want to fit the mass function, right? And in the galactic field, they had fit a single power law to their data. So we do the same thing here. We're going to fit a single power law, again, in linear space where the number goes as m to the minus alpha. And what we do is we sample this parameter, alpha. We make a fake population for every sample, and then we project that fake population into color magnitude space, assuming this evolutionary model. And so we can calculate the likelihood of each model given both our sensitivity and our true detections, and identify what the best fitting mass function is. And what we get is this alpha to the 0.3. So again, we do have that increasing mass function to the 0.3, and it's consistent with what had been seen in the galactic field population. However, if you just look by eye at our color magnitude diagram, it doesn't look like the mass function continues down to a Jupiter mass. It looks like there's nothing below 3 Jupiter masses. So we tried various other models to better fit these data. We tried a log normal, we tried a normal, we tried a single power law with a cutoff, and we even tried a double power law model. And the only one that seemed that actually fit the data better based on our Bayesian evidence is the double power law model. We define this here as m to the minus alpha, again, for one of the low mass portion of the mass function and the high mass portion of the mass function, again in linear space, where the mass at which these two power laws differentiate is also a free parameter. And when we fit that to the data, what we find is that for the low mass end, we have a power law index of -1. And for the high mass end, we have a power law index of 0.3, where the breakpoint mass, that mass which they differentiate, is around 12 Jupiter masses. And this looks something like this, where in linear space, we are increasing the mass function from around the substellar limit down to about 12 Jupiter masses. And then we have this turnover in a decrease down to our sensitivity limit at half of a Jupiter mass. Now, I will say that we have relatively high errors here. We don't have a really large sample size to characterize the mass function. And this red shows you our 1 sigma error bar. But this is still identifying the first turnover in the mass function in a stellar population to date. What we can confidently say is that the mass function does not continue to rise as we go to lower and lower masses, that it's either roughly flat or decreasing. And I want to point out that we're sensitive down to about half of a Jupiter mass, which is below our theoretical limit of fragmentation, and we don't find any likely cluster members down to 3 Jupiter masses. Importantly, we're not claiming that the opacity limit is 3 Jupiter masses. What we're claiming is that the mass function is decreasing as we go down to lower and lower masses, which had not been found before. So it is possible that you could form a 1 Jupiter mass thing directly through fragmentation, but given our results, a 1 Jupiter mass thing would be significantly less likely to occur than a 3 Jupiter mass object, and a 3 Jupiter mass object would be a lot less likely to occur than a 10 Jupiter mass object. Again, we do have a small sample size, so we do want to expand our sample, place much stronger constraints on this population, and really nail down what is the opacity limit and what is the shape of the IMF as we go to lower and lower masses. Fortunately, we were awarded cycle 3 time to follow up our sources that we identified as cluster members to obtain near-spec prism spectroscopy of all of these sources between 1 and 5 microns. And at the same time, we obtained coordinated parallel NIRCam imaging in the periphery of the cluster. So if we think that environment may play a role in the formation of planetary mass objects, it's possible that proximity to high mass stars, which there are a few in the core of this cluster, it's possible that proximity to these high mass stars could suppress the formation of very low mass planetary mass objects, and that they're more likely to occur away from where you have increased turbulence and increased feedback in the periphery of the cluster. So one of the things we want to do is both place better constraints on the mass function, but also explore intra-cluster environmental differences. So we are still working through these data, so I can't give you a full characterization of what we have so far. But what I can show you is one of the examples for our near-spec spectroscopy. So here is a 10 Jupiter mass object that we estimated from the NIRCam photometry. This is just the photometry that we had from NIRCam and our 8 filters that we used. And here is the near-spec spectra. One of the things that should probably pop out right away is that the flux in the near-infrared is significantly depressed. That's again because there's so much extinction in this region. But if this is one of these planetary mass objects that we suspected, we expect to see, for these low temperatures, water absorption features in their spectra. And we do. We start seeing that in the near-infrared spectra here, here, and here. And so this is definitely one of these low-mass planetary mass objects that we had identified. And we are currently working through all of these data to better constrain the masses of these objects and better characterize the IMF. On top of that, we got this NIRCam peripheral imaging, and just in time for the cycle 5 deadline, we did analyze all the point sources in those data and identify a handful of really interesting candidate point sources that could be consistent with free-floating Jupiter mass or 2 Jupiter mass objects. In these data, given our constraints from our primary observing of NIRSpec, we could only collect data in 2 filters. So we don't really have a good characterization of what's definitely a cluster member and what's definitely not a cluster member. Just by looking at this, you can also see that there is a population of background objects that are pretty clear here, but it's much less clear as we approach our evolutionary models, right? So we definitely need to get near-spec follow-up spectra of these sources in order to better constrain the IMF, to confirm whether or not these are cluster members, and to see if there are any intra-cluster environmental differences. One of the last things I want to point out about the IMF here is that because our result shows this decreasing mass function, I think this, if we think about the process of the limit of turbulent fragmentation, it makes sense that we should start producing lower and lower mass objects. Because in order to make a 1 or 3 Jupiter mass object, we need to have a very tiny prestellar core that can survive. And because these regions are turbulent, because there is feedback, it is a frequent occurrence where you can make prestellar cores that never turn into anything and then get disrupted and just are no longer prestellar cores. So to make things that are lower and lower mass down to the absolute limit of fragmentation, it becomes harder and harder for those to be stable. So we do see that decrease. And hopefully with follow-up work, we can have a significantly larger sample and place even stronger constraints on the IMF. Now, the IMF is one of the outcomes of the star formation process. However, binaries and multiple systems are another outcome of the star formation process. And these are very, very common occurrences. Binaries are just when 2 objects are bound together within the same system, and multiples are when more than 2 objects are gravitationally bound within the same system. And this is a very common occurrence. You may hear that half of all stars are in binaries, and that's roughly true. About half of solar-type stars have a stellar companion. And we make binaries through 2 dominant mechanisms. The first mechanism is turbulent fragmentation, which I have been talking about already today. But within the envelope of one of these protostars, you can have multiple fragmentation events that make multiple protostars. And so we can have binaries that just form directly through this process. But we can also have binaries that form through disk fragmentation, where we have a very young protostar, probably with a class 0 disk, so it has a large disk. And that disk can fragment and produce a core that then goes on to accrete material from the disk of its host and build up its mass. And subsequent processes can absolutely affect the primordial binary characteristics of these systems. So for example, widely separated binaries that form through turbulent fragmentation can migrate to closer and closer separations just through interactions with a gas in their envelope. Simulations show that they can move from thousands of AU down to even just 1 AU in separation. And from the disk fragmentation case, the companion can actually accrete preferentially material from the disk, sequestering that material that the primary can't accrete, building up the companion's mass relative to the primary. Other processes that are environmental dependent can also alter and disrupt initial binary configurations. For example, in a very high density region, because there are going to be a lot of stellar encounters, stellar flybys, weakly bound binary systems can just be disrupted, and that binary system can just become two single stars that are remain in that region. So there are definitely environmental processes that can play a significant role in the formation of binaries, and importantly, stars form in all different types of environments. They can form in low mass, low density associations like chameleon or Taurus that have maybe 100 or 150 stars. They can form in embedded clusters like NGC 2024 that has hundreds of stars and is at intermediate density. They can form in high mass, high density bound clusters like the Orion Nebula cluster or the ONC. It has thousands of stars and is likely bound. But they can form in superstar clusters and globular clusters and OB associations and everything in between. There is a wide variety of different star forming environments, and they all will populate the galactic field. So stellar associations will essentially just drift apart from each other, and those stars will just become a part of the field. But even bound clusters will throw out a significant fraction of their stellar population over their lifetimes. So in order to understand the galactic field population, we really do need to understand the stellar populations within star-forming regions. So one of the questions that I have is, does multiplicity depend on environment? Are there strong impacts on multiplicity that we see as a function of environmental properties? And does that tell us something important about the field population? So this is not a new question. This has been something that has been studied before. And here on the right, I show a figure from a recent review by Stella Offner that shows the wide binary fraction as a function of primary mass. And I want you to only focus on the blue point, the red point, and the black points. The black points are from the galactic field, and this shows the frequency of stars that have companions at separations between 100 and 10,000 AU, so out to very wide separations. And what we see is in Taurus, which is one of these low density associations, there is significantly higher companion frequency than we see in the galactic field. And the field even has a higher companion frequency than the ONC at these wide separations. Now, this can be directly attributable to dynamical interactions from the such high densities that exist in the ONC, breaking apart these widely separated, weakly bound binary systems. Essentially, there are no binaries in the ONC beyond about 600 AU. But this is only a result that we can see in these two regions and for solar type stars. So some of the questions that I have about probing various environmental impacts on multiplicity are companions at closer separations, less than 100 AU, impacted? Does this trend continue across all masses? Do we see the same thing for low mass stars, which are the most common type of star? And does it continue to trend across all environments? So do we see this in different types of regions? Is there just one environmental factor that controls this? Are there many environmental factors? These are important things that we need to understand, also to understand the galactic field population. So to do this, we need to explore more common and more diverse regions. These regions include these low-density associations like Taurus that have been characterized by Adam Krauss back in 2011. But they also include embedded clusters that are these young intermediate density regions that will become unbound once all the gas in the region is dispersed, like NGC 1333 or NGC 2024. We also want to probe high-density regions like the Orion Nebula cluster, where we did see environmental differences before for the very wide population. And we can also probe OB associations, which are pretty common star-forming environments. And present day, they have low density and are unbound. But they could emerge from dense embedded clusters that could have had dynamical processes play a role at early times. Or they could form in situ, where they have very low densities and they don't have any dynamical interactions. So by looking at the multiplicity in these regions, we can both understand about the origin of these regions, but we can also better understand the galactic field population. In some of these more dense regions, like NGC 1333 and NGC 2024, we can use wide field diffraction limited imaging to probe these star-forming environments. This work is currently ongoing, so I won't be able to give you results in these regions just yet. But we can also probe these larger regions using things like Keck and Gemini. Now, there are hundreds of solar type stars that exist in these different types of regions, and we probably won't be able to get tens of nights on Keck to observe hundreds of solar type stars in a few star forming regions. So in order to carry out a multiplicity survey in these regions, we first want to select our sample, so picking these kind of these solar-ish type stars in these three star forming environments, the ONC, Orion OB1A, and Orion OB1B, which are two OB associations. But instead of observing all of the stars across that mass range in this region, we will first pre-select the stars to observe with Gaia using its excess noise statistic. So there's this value called the RUI, or the residual unit weight error, that characterizes how well a single star astrometric solution fits the data. And past work by other people have identified that an inflated RUI value maps pretty well into separation and contrast space for companions to stars. This is work from McKenna Wood that gives the color map is your log RUI value. And what they had identified is anything above a RUI value of 1.2 likely has a companion that can be mapped into this separation and contrast space. So we are only going to observe sources with a RUI value greater than 1.2 using Keck non-redundant masking and Gemini speckle interferometry to resolve these companions, to both confirm that they exist as true companions and to understand their true separations and mass ratios. We go about this kind of in a tiered way. We first identify the population that has this excess RUI value, which is about 20 to 25% of the population in these three regions. Then with Gemini, we observe everything with a RUI greater than about 2.4, which is consistent with what Gemini speckle is able to resolve. And then with Keck, we observe everything with a lower RUI between 1.2 and 2.4, because Keck, we can resolve things at fainter contrasts and at closer separations. Okay, so to date, we have observed and detected 60 companions to 72 stars that we observed with Gemini speckle interferometry. Here on the right, I show the detection probability from the contrast curves from our Gemini observations for the full sample of 72 stars. And then the red circles show the separations in mass ratios of the detected companions in these three regions. We also observed 60 stars with Keck imaging and non-redundant masking, and that analysis is currently ongoing. So I don't have results for Keck yet, but we do have our Gemini results here. And with these observations, we have a total sample size of almost 600 stars with only observing about 130 sources. So with observing about 20-25% of the sample, we can make these really large multiplicity surveys and place strong constraints on the companion properties. Even though we don't have the Keck results yet, I can still do some preliminary analysis of the demographics in these regions. I do have the Gemini results here on the left, our detections and the sensitivity. But because everything we observed with Keck had a RUI value less than 2.4, we know that they shouldn't have companions that exist at the separations and mass ratios that map to Rui values greater than 2.4. So for here, we can assume that these sources observed with Keck have non-detections over this parameter space. And so this is our detection probability that we can incorporate for the Keck sample and the unobserved sample. So when we combine all of this together, this color map shows our combined survey detection probability with our Gemini detections. And we can characterize the companion frequency with our Bayesian demographic analysis, where we use Poisson statistics to calculate the companion frequency and correct for incompleteness given our detection probability maps here. So for our preliminary results, we find that the solar type population in Orion OB1A, OB1B, and the ONC are all consistent with the solar type population in the galactic field. So over separations of 18 to 480 AU, which is more than 4 times closer than those previous studies at wide separations, and mass ratios of 0.2 to 1, we find this consistency. Here on the right, I show the companion frequency over this parameter space for the field, the ONC, Orion OB1A, Orion OB1B, and Taurus. Now, this Taurus sample is from work done in 2011. And if we just take their population that matches these criteria, so 0.55 to 1.4 solar masses and mass ratios of 0.2 to 1 and separations of 18 to 480 AU, what we find is that the Taurus population actually has more binaries than the field, the ONC, and Orion OB1A. And it's consistent with Orion OB1B, which is consistent with all the other ones, but that's also because it has a relatively large error bar. So just straight from this, what we can tell is that there are environmental impacts that affect these binary populations, at least within the parameter space that we were currently probing. We see that the ONC and OB associations are consistent with the field, but that Taurus has significantly more binaries than at least one of the OB associations in the ONC. And what that means is that there's likely dynamical interactions that break apart widely separated, weakly bound initial binaries in these regions that still exist in Taurus because it's so low density, you don't have any of those dynamics. Now, I want to also extend this down to lower masses. So previously probed the solar type population, now we want to extend down to low mass stars. Importantly, because they are the most common type of star. So most stars are low mass stars. So in order to understand star formation properties, we really need to understand the low mass population. To do this, I'm going to look into the Orion Nebula cluster, mostly because this is a very well-studied region that has just a ton of data already collected for this star-forming region. There are multiple spectroscopic programs that have characterized cluster members in the ONC, and there's also HST treasury programs that have performed these really large mosaics with wide field imaging, and that is also diffraction limited. So we can resolve very close companions using these types of data. And to do this, what sorry. Before I get there, what I want to say is that we only targeted the low mass stars with the HST data because all the solar types were saturated. So we couldn't probe down to close separations for the solar type population, only for the low type population, or for the low mass population. So that's why I'm only focusing on low mass stars here with the HST data. So to find these companions, we're going to use empirical PSF fitting. And here there are models of the actual point spread function on this detector in question, the advanced camera for surveys, as a function of location on the detector. Here I show some example detector sampled PSFs that correspond to different positions on the detector. So for example, in this bottom left corner, you have this a PSF here that is resembling one in the bottom left corner. The PSF in the center of the detector, top right of the detector. And what we can see is that the PSF structure changes very significantly for ACS as a function of position. And using empirical models, we can place really strong constraints on the ability to detect companions because the PSF is so well characterized. This is work that has been done by Jay Anderson that observed globular clusters that have many thousands of point sources all across the field of view, who then built these super sampled, these 4 times super sampled PSF models that we can use here. And what that really means is that we have 16 pieces of information for every single pixel on the detector. So we can build these models that we can finely fit at subpixel, various subpixel positions. Using these models, I created a double PSF fitting code. So instead of subtracting a single PSF fit and looking in the residuals, I instead simultaneously fit a double PSF model, which will allow us to resolve companions at closer and closer separations. And to characterize our sensitivity, what I did was I made a bunch of artificial binaries at various separations and contrasts for many signal-to-noise values for all the filters that we used in question. And I also made many artificial single stars and ran our double PSF fitting code on both the artificial singles and the artificial doubles. And what this figure shows here is that the black points are the best fit binary solutions to the artificial single stars, meaning where our code will converge around a known single, so the false positives. And we also mapped out the parameter space where we are likely to recover known injected companions. And this red line shows you our sensitivity. So with ACS, for a relatively bright point source, we can detect companions down to about 1/2 of a pixel in separation, which at the distance to the ONC is about 10 AU. So we're probing down to these closer and closer separations. Now we have our population of sources that we identified in the data from previous spectroscopic analyses, and we can run our double PSF fitting code on these data. And what we find is 44 companions to 276 low mass stars in the ONC. Each of these images has 3 panels. The top panel is a cutout from the data, straight from ACS. The middle panel is my binary PSF model, and the bottom panel are the residuals. And for everything in this bottom row, you can see that these are binaries by eye. They're very obviously binaries. You can tell just by looking at them. I can tell by looking at them, and the code picks them up very easily. But for everything on this top row, these are all things that I can't tell are binaries by eye, but they're binaries with separations between 1 and 1.5 pixels in separation. So these are very closely separated binaries down to the diffraction limit that we're able to detect with our code. Okay, so we made all of our detections here for our full sample. We know our completeness because we've very thoroughly characterized our sensitivity to companions, and now we can perform the same Bayesian demographics to characterize the companion population. This time, yes, I'm both estimating the companion frequency for Poisson statistics, but then also characterizing the mass function by fitting a power law model to the mass function of our detections. And what I find is that for low mass stars, the ONC is like the field. It has a companion frequency over all mass ratios in separations of 10 to 200 AU that is consistent with the galactic field population. And on top of that, the mass ratio distribution is consistent across the ONC, torus, and the field. So what that means is that if we do expect there to be more companions at wide separations in torus, then the ones that are being disrupted in the ONC are likely just these wide ones and not the low mass ratio ones. So it's probably just a function of separation here. But importantly, we see a consistency between the ONC and the field for low mass stars and for solar type stars. And we see that across several different regions. And with the last few minutes I have here, I want to extend this to substellar masses. So in that same HST data, yes, we can probe the low mass stellar population, but we can also probe the substellar population. From previous studies of brown dwarfs looking for companions, in the field, what we know is that companions almost all exist at very close separations, around 1 to 10 AU, and that at separations greater than about 3 AU, which is roughly the sensitivity limit for most of these surveys, the companion frequency is somewhere between 10 to 25%. And beyond 20 AU, the companion frequency is less than 1%. So very few brown dwarfs have companions at separations wider than 20 AU in the galactic field. On the other hand, in star-forming regions, we know very little because sample sizes are always very small. If we have a region like Taurus that has 100 stars, it has somewhere around 20 brown dwarfs or so. And a population of 20 is very small and not very good at getting you strong constraints on statistics. So we go back to the ONC, this large star-forming region. We know the population. There are a lot of spectroscopic programs that have identified brown dwarfs. We identify those in the HST data, and we analyze them with our double PSF fitting code. And here we identified 7 wide brown dwarf binaries, all with separations greater than 20 AU. Here I show 5 examples from our data. And this tells us that the companion frequency in the ONC for wide brown dwarfs is greater than that in the field. The field barely has any wide brown dwarf binaries, but we see them in this young 2 million-year-old cluster. So we can conclude that wide brown dwarf binary formation is a more common outcome of the star formation process, but it doesn't really exist in the galactic field. And that's because dynamics probably break up a lot of these binaries over the next several million years, given their very, very low binding energy and given the very high density of the ONC. But importantly, these are more common outcomes of the star formation process than we had ever thought before. And we can start placing that constraint because we can do these large multiplicity surveys. Now, in the field, the last thing I'll say, in the field, that as we go to lower and lower temperatures, on average, that also means we're probing lower and lower masses. So brown dwarfs have this mass age degeneracy, where if we don't have strong constraints on the age, we don't really know what the mass is. But on average, if we go to lower temperatures, we're also characterizing lower masses. So one of the things that we can do with JWST is look at these Y-dwarfs, these very low temperature objects. They have effective temperatures less than 500 Kelvin, and most of their flux is around 4 to 5 microns. We can use JWST to look for companions to these objects for the first time and really constrain see if binaries even form around these very low mass objects and exist into the field. And from several programs that have looked at Y-dwarfs with NIRCam and MIRI, we have detected the first 2 Y-dwarf binaries with NIRCam and MIRI. The one on the left, WISE 0336, is at a separation of about 1 AU. WISE 1935 is one I just found very recently, is at a separation at about 2.5 AU. And these are the only 2 Y-dwarf binaries we ever have detected so far, and are really examples of multiplicity continuing down to the lowest and lowest masses that we've been able to probe so far. So with that, I want to put up my summary slide. Thank you very much for having me, and I'm happy to take any questions.
Questions for the audience?
Yeah, on one of the plots you showed some of the potential masses for these very substellar objects. It looked like the variation was like up to a factor of 5 for different tracks. Could you talk a little bit about how that folds into then your uncertainty of where the break is and the slope?
Yes. Okay, yeah, great question. So I think you mean...
It was a blue and a red curve.
Yeah, this one. Yeah, so this is, these are 2 different evolutionary models. One of the things is that this is an extremely low surface gravity. To give an example of the absolute lowest mass these objects are likely to be, for the most part, we expect them to be slightly higher, about 3.5, a surface gravity about 3.5, which is more consistent with this ATMO 2020 1 million year old curve. I agree that the uncertainty in the models will propagate to the mass function. But given that we characterize the shape of the mass function, the uncertainty in the model will really tell us, places uncertainty on that breakpoint mass. So it places uncertainty on the value at which these differentiate, because this is a shape argument, really, right? Yeah. So if these models are, under predicting the mass, then this would be shifted for sure. And hopefully we can get much better constraints on the masses of these objects with improved models and improved spectra of these sources. But it shouldn't change the fact that there is a turnover, just the breakpoint mass.
Okay, thank you.
Hey, Matthew, really nice work. So I just wanted to point out something that I don't know if you saw, but with Max and one of his students, Caleb Eastland, we had a paper that covered some of the discrepancies in some of the torus AO samples that are mapped. So I guess I'm just wondering, is any of the stuff that you're doing, so I guess that error in or the discrepancy with the torus point, I'm wondering if that would still hold if you used the corrections we have in that paper, and whether or not the Gaia subset of Rui targets is also going to suffer from this magnitude limit problem.
Yeah, this is a great question. What I'll say is that the lower mass objects will be the ones that will most suffer from this bias, which is why I really didn't quote that when I was talking about the lower mass population. And we are here comparing across separations out to about 500 AU. And if I remember correctly from that recent paper, you still do see an excess beyond about 100 AU, but within 100 AU, you don't see an excess. So I think if we were to constrain this to closer separations, not within 100 AU, we would have larger error bars, yes, but perhaps these would be consistent. And that's something I'm definitely looking into before we would publish these results.
Okay, because I guess my concern is that we preserve the wide binary deficit in the ONC, but the excess between, at several tens of AU, which is on the inner side of your sample, might go away. So
right.
That's what I think might bring the torus part down, because that is basically the discrepancy is at the peak of the distribution function. So changing that lever arm is probably the most important for the integrated companion frequency.
Yeah, absolutely. I think if we were to draw a line here at 100 AU, we might see consistency. And the thing is, I do wonder, our error bars would kind of blow up a little bit here. But yeah, I think you're right that below 100 AU, they'll probably be consistent. But at these slightly wider separations out to 500 AU, there still does appear to be this discrepancy.
Right. And then I guess my other question is, so what about with the Gaia Rui sample? Are you at risk of being of having a problem by introducing the magnitude limit there?
Right. Great question. So we didn't look at the lower mass objects that we think are going to be biased in these regions. We only looked at the higher mass spectroscopically confirmed sources. So we don't think we're going to be limited. We don't think we're going to be limited, the magnitude limited there, because we did not look at that fainter end that is probably incomplete.
Okay, but and so you're saying, but even for the solar type stars, are you not biased by which ones are spectroscopically confirmed because they were brighter and less extincted?
I don't think so, because the imaging surveys that identified these sources went a lot deeper.
Okay, great.
So, they go down to like 0.25 solar masses, and we were pretty sure that we're complete for these solar types.
Hi, Matthew. Thanks for the great talk. So my question is, so you did the Gemini speckle imaging survey. Can you do the mass ratio measurement for those from those images?
Yeah, so this is a great question. So these are actually corrected for, so we do have mass ratio estimates here. I didn't want to place a constraint in the mass ratio distribution here without having done the Keck analysis, because the Keck analysis should be sensitive to lower mass ratio sources that could populate, for example, this portion of the parameter space and this portion of the parameter space. So I felt like it would be biasing the mass ratio constraint. So I only did the companion frequency. We do just take the photometry from Gemini speckle and use that contrast to estimate the mass of the companion. And we have some pretty good color correction, like matching into evolutionary models to make sure that we can use those narrowband filters from speckle interferometry to get relatively decent masses.
Are they like highly extincted? Because most of your targets are in the heavily obscured field. Because your targets are selected from the JWST imaging survey.
So for the multiplicity survey, these are not selected from NGC 2024. These are different regions, and they have significantly less extinction. So Orion OB1A and OB1B are roughly 11 and 5 million years old. So there's really not very much extinction there. And the ONC, on average, it has, a magnitude or two of visual extinction. But it's definitely not severely extincted like we saw in NGC 2024.
Thank you.
I would like to ask a question that we were chatting just before your talk. All the way for the NGC 2024, the low mass limit, could you actually comment on those that were removed because there was contamination?
Yeah.
Remember, we see that the lowest mass we see the 3 solar mass and higher. So Jupiter mass. So you did not actually detect anything under 3 Jupiter mass while you were sensitive to Jupiter mass. So most of them were removed. So I would like to hear about that process, actually, how.
Absolutely. Yeah. So what we did was we took a galactic field population model, and we projected that into color magnitude space for the filters that we were using. Then for every one of our point sources that we had identified, we have an extinction estimate from Herschel observations. So we use that extinction estimate combined with the galactic field population model and calculate the likelihood that the colors, the photometry of this source are consistent with the photometry of that population. And for about half of them, they were very consistent with a background star population. And for about half of them, they were very inconsistent with a background star population. So that's how the process went.
Yeah, we have one more.
Thanks, Matthew. I had a question for the double PSF fitting. Are you able to determine that the close point sources in projection are physically associated, or is it just, is there a risk of chance alignments like some of the jumbos claimed in Orion?
Yeah, right, for sure. This is a great point. We were very careful about estimating our chance projections, which is why we only surveyed out to about 200 AU in separation. We were able to take the source density estimates from the point source catalogs in the ONC from these same data and estimate the likelihood of a chance projection just given the stellar density in the region. So from there, we estimated that we have about probably 1 chance projection across the 10 to 200 AU separation regime. And if we were to go out to further separations like 500 AU, for example, we would start to have a lot of these chance projections, which is what happened with the jumbos that you were referencing there. But yeah, because we used the source catalog already made for these regions, we have a really good idea of the source surface density. So that went into our calculations as well. So we think that almost all of our detections are very likely to be physically associated.
Thanks.
I don't see questions in Zoom. Okay, so next thing again.